Well, it's a great privilege to talk to you after all these delays that we've had.
Mm-hmm.
So, rainbows, halos and glories. Right. This is where it all started for me. When I was a PhD student in the physics department at UMIST, I was lucky enough to go to Yellowstone Park on 3 winter occasions, expeditions to Yellowstone Park, to make use of the ice crystals, which are generated from Old Faithful and the geysers that go off every so often. My apparatus is at the bottom of the screen there, but what I'm talking about is this glow on the left of the screen. If I move and use an arrow, can you see that?
Oh yeah.
Can you see some highly reflective region on the left-hand side of the screen?
Yes, we can see that, and we can see your mouse as well.
Oh, brilliant! That's what excited me about atmospheric phenomena, and those are ice crystals, and the sun is shining off them, and they're reflecting in a certain way, and hence my whole interest in rainbows, halos, and glories. Now, we all know that the sky is blue, and that's because the blue light gets scattered the most. Lord Rayleigh pointed that out to us. And of course, this is different. When you've got the sun setting over the horizon, then it has a great path length, and all the blue light has been scattered out, leaving it red. So we see, one of the things we see in the sky, beautiful red sunsets when the blue at the end of the spectrum has been scattered out. This was a picture from my back garden, actually, and the clouds are generated over the power station up near Liverpool. Fantastic red sunsets. Of course, the blue is all missing. Now, this is something that most people will not ever see, and I've seen it once. This is the green flash for the setting sun, and you have to see it over an ocean surface, a very calm ocean surface. The sun is setting in the distance there, and the green flash, you can see it in the bottom picture there, but this is a sequence of the green flash from the start of the sun setting to the bottom right picture where it's setting, and you can see the green flash. And the green flash is there because it's the last piece of light from the sun that gets refracted through the dense atmosphere just to get to us. So it's a well-known optical phenomenon which hardly anybody has ever seen. Now, the atmosphere, this is just a summary of the atmosphere. We've got the altitude vertically on the left, and we've got a line which shows a diagonal, a zigzag line across the picture, which is the temperature. And obviously clouds are formed in the bottom region of our diagram, where we have this temperature decreasing, and then suddenly there's a reversal, and the temperature in the atmosphere rises, and we get this series of rising temperatures, and we get various sorts of clouds that we'll be talking about as we go through the talk. So here are some typical clouds. It was Luke Howard back in 1803 who came up with the names of cirrus, cumulus, stratus, nimbus. And here are a few pictures of them, a beautiful thunderstorm on the right here. And we've got cirrus clouds up here. We'll be talking about these rings later on. And we've got altocumulus, meaning they're halfway up, nimbostratus, which are thunderstorms, and so on. Now, every so often, a new cloud type is discovered. And there's an association called the Cloud Appreciation Society, and it was started by this chap, Gavin Pretor-Pinney, and he spotted this cloud, which he gave the name Undulatus asperitas. And after many, many arguments with the Royal Meteorological Society, he finally got them to agree that this is a new type of cloud, because they wanted to tell us that it was this sort of cloud, which is a well-known mammatus cloud, that you get hanging below thunderstorms. But then he showed them that one, and they said, oh, that's new. So Undulatus asperitas is now an accepted new type of atmospheric cloud. Now, how do clouds form? Well, little pieces of dust in the atmosphere called cloud condensation nuclei, water vapor in the atmosphere deposits on them to make water droplets. Now, you would imagine that you would get a range of droplets of various sizes, and that's what happens. And the larger ones collect the smaller ones, and eventually you get a raindrop. typically 2 millimeters in size. There's a lot more physics to that than I've just said. And we get ice crystals. When the temperature is low enough, ice crystals form, and these are particular snowflakes which have reached the ground and were photographed by these Bentley and Humphreys, very keen snow crystal scientists back in 1931. And there's a lovely coffee table book of their snow crystal pictures. And more modern picture, Ken Lebrecht is well known for taking fantastic pictures of ice crystals in his microscope, polarized light. So here we get a table showing the different types of ice crystals in the atmosphere, which change with temperature. So we've got these long columns, we've got these flat plates, and then you get on the corners of these plates, you get these dendritic branches growing out to make snowflakes. So these types of crystals are all temperature dependent, and they all grow in the atmosphere in different temperatures. So if you see a thunderstorm and over the top of it, you see this wispy layer of cloud, this is called a pileus, and the wispy nature of the cloud tells us that it's made of ice crystals, whereas the sharp edges of the cloud show us that these are supercooled water droplets. So even though we're up at very low temperatures, the water droplets haven't frozen, they become supercooled. So a sharp-edged cloud has got supercooled water droplets, but a fuzzy-edged cloud, these are ice crystals. And here's a picture of a thunderstorm with the anvil, the well-known anvil, and these are the fuzzy regions of ice crystals and hard regions of supercooled water droplets. And this one is taken by the astronauts in the space shuttle. So the anvil is really huge. Now these ice crystals obviously interact with light and cause refraction. So here we have these three types of ice crystals, the plates, the columns, and a column with a bit of a funny end on it. Now, here is the cross-section of a hexagonal ice crystal, and here we see the beam of sunlight coming in. It's refracted at the first surface and refracted against at the second surface, and there's a 22-degree angle between the straight-through beam and the refracted beam. Now, for this type of plate ice crystal, the light's coming in and hitting the basal face, the bottom face, refracted here and refracted again, and it's deviated by 46 degrees. And similarly, both of these can happen if you've got a long column crystal. And these types of crystals are responsible for all the optical effects we're going to see now. Now these are moon dogs. Here on either side of the moon, these are called moon dogs, and they're caused by light being refracted in horizontally oriented ice crystals. It's quite a spectacular picture. And here we see it in a sun. The sun with its moon, with its sun dogs on either side. And the thing is that this 22 degrees deviation is the angle that is subtended between the sun and the sun dog, and the sun and the sun dog on the other side. So 44 degree spread, 22 degree halo, it's called. Now this one I'm very proud of. This was taken from my garden. So anybody can look up and see a sundog if you've got the right conditions. It's during the late afternoon, the sun is setting, and on either side of the sun, or maybe just on one side in this case, you'll see this orange-red glow, which is a sundog. Now, if you go to the Arctic, you can take some fantastic pictures of all these arcs. Here we see the 22-degree halo. Here we see the sundog, or parhelia. Here we see an upper tangent arc, which is due to different sorts of crystals. We've got a superlateral arc. We've got the parhelic circle, which goes right around the horizon. And we've got the circumzenithal arc, which goes around the point directly above your head. Another picture. Here's the 22-degree halo. This one out here is the 46-degree halo. You remember one of the crystals deviates by 46 degrees. This is the British Antarctic Survey Building, which they have on struts so they can raise it when the snow depth gets to a certain depth. They have to raise the building. Now this one also I'm very fond of. This is a circumzenithal arc. I was sitting in the garden looking up at the sky, and I saw this directly above me going around the sun. And this happens quite a lot, but most of us don't look upwards very much. We tend to walk around looking where we're going. But if you walked around with your head peering up at the sky, you would see all sorts of wonderful optical phenomena. Now you get the 22-degree halo around the moon as well as around the sun. And this one is a 22-degree halo with an upper tangent arc, again produced by ice crystals. Now, to forget this black object out here, what I want to show here is a sun pillar. Here's the setting sun, and this bright vertical column is the sun pillar. And this is a very interesting illumination. Ice crystals, when they're falling, and they're not usually as big as this, of course, but when the ice crystals are falling, they fall horizontally. The aerodynamic drag causes them to have a horizontal orientation. And so light can be reflected and refracted by these, and it gives you the sun pillar. Now, most of my life at university, I was studying thunderstorms and how they become electrified. And here we have a fantastic lightning stroke to the Eiffel Tower. Sacré bleu, it says up at the top. Now, thunderstorm research took a lot of steps forward when Benjamin Franklin was brave enough to fly a kite up into a thunderstorm. And he had the other end of this wire from his kite went down into a very primitive battery called a Leyden jar. And he found that sometimes the electric charge coming down was positive and sometimes it was negative. And this is one of the mysteries of thunderstorms. Why do we get these positive and negative effects? He survived. A Russian chap who tried the same experiment was fried, I'm afraid, and didn't make it. So don't try that at home. Now, which way does lightning go? Well, what happens is it tries to find its way to Earth, and these are all paths that try to find their way to Earth, but didn't make it. This big one, it did make it. And as soon as it made it, that's when the charge started to flow. And what happens is that the charge starts to flow at the bottom, and the brightness of the lightning strike moves upwards, but the charge is moving from the cloud downwards. So when people ask you which way does the lightning go, well, it goes both ways. It depends if you're talking about the brightness moving up or the charge moving down. So here's some data. Basically, the bottom line is it takes 5 seconds for the sound of the thunder to reach you, but obviously you see the lightning pretty quickly. So you can tell how far away it is, 5 seconds per mile or 3 seconds per kilometer, if you prefer. You get various channels, various steps. The leader coming down comes down in steps, but once it's made that conducting wire, conducting path between the thunderstorm and the surface of the Earth, then you have what's called a return stroke. And this is the very bright streaked stroke that you see. And there can be several return strokes. There could be up to 5. And you sometimes see lightning flashing, very, very quickly flashing as 5 strokes come down the same channel. The current is 15,000 amps. It heats it up to 30,000 degrees. This is a good place not to be in a thunderstorm. Many people in America get struck on golf courses that have a lot of dangerous thunderstorms and a lot of golfers. Now, what produces the lightning? Well, it's hailstones, small hailstones called graupel. And here's a graupel particle falling in a thunderstorm. And it's bumping into water droplets, which it collects so that the graupel is getting larger and larger. It's also colliding with ice crystals, which collide and bounce off. And during that brief moment of contact, electric charge is transferred, and the graupel sometimes becomes positive, sometimes becomes negative, and the ice crystal takes away the equal and opposite charge. So a thunderstorm is charged up like this. We have a negative region and a positive region. This is being generated by these interactions between ice crystals and hailstones, and this is being generated by the opposite sign of charge transfer further down. So this is called the thunderstorm dipole, And sometimes you get this extra positive at the bottom, so it's a thunderstorm tripole. But basically, negative charge is coming down in that lightning stroke. This is the conventional thunderstorm lightning discharge to ground, bringing negative charge to Earth. But sometimes it can come from the positive side, which is why Benjamin Franklin sometimes said it was positive. So some spectacular pictures of lightning, of course. This is rushing along underneath the thunderstorm. And you can get this thing called the bolt from the blue. This is the one that's unexpected. So you can be sheltering from a thunderstorm, miles away from it, and then something will come out of the side. And this is this famous Iceland mountain glacier, the eruption a few years ago, which held up all the air traffic. And here's one of these lightning bolts that comes out of it and goes back in. So it's a big mystery how these storms get electrified. And it's believed that might also be due to ice, but it's still very controversial. Now, sprites. These are sprites, and very few of us will have seen sprites because they happen they're only visible many miles away when the thunderstorm is very low on the horizon, and they happen up in the air way above the thunderstorm. And you can see these various effects. We've got blue jets, giant blue jets. These are the sprites. The red are the sprites. Halos, and this isn't the same as the ice crystal halo. This is just because it's circular. And this was a photograph of some of these sprites, which are absolutely spectacular. And they have been photographed in the United Kingdom, but usually most of the pictures come from the United States, where you've got large areas of flat land and thunderstorms could be 100 kilometers away. And so you get a good view over the thunderstorm. So here we see the thunderstorms down here. Here we see the positive lower region of charge. This is a positive discharge to Earth. When that happens, the sprite way up here happens. It goes into sprite mode. And again, nobody really knows quite why. You get an upward flash from the top, and pilots, of course, were surprised that the scientists didn't know about this, because pilots see these things all the time, but scientists don't go flying very often, so we haven't seen these. And there's a super one going up from the top, which you might find. You might be able to photograph one if you were lucky enough to be in the right place at the right time. Blue jet. Now, optical effects in water droplets. This is what it's all about. Here we have the Newton prism, white light coming in, refraction at the first surface splits it up into colors, refraction at the second surface splits it up into the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. Richard of York did something in vain, I can't remember. Roygbiv, anyway.
A battle in vain, isn't it?
That was it. No. Right, a typical rainbow with the colors of the rainbow there. Now here we see something that's rather unusual, a double rainbow, and the dark patch between is called Alexander's Band. I think there's a famous tune about it. But this is the normal rainbow, and sometimes you see the double rainbow. Now, why is that? Right, well, here's a prism, and this is the typical breaking up of the white light into all the colors of the rainbow. And here at the bottom, we have a water drop, a raindrop falling, sunlight coming in, being broken into its colors, being reflected inside, and then being refracted out with the rainbow colors. So in order to see a rainbow, you have to stand with your sun, with the sun behind you, and you'll see the rainbow directly ahead of you. Now, the question was, why do you sometimes see the secondary rainbow? And this is the reason. The light is being refracted, reflected, reflected again, refracted back. So this is a double refraction, and this is what gives you the secondary rainbow outside. And there was a question in New Scientist only a few months ago, which said, how many rainbows are theoretically possible? Well, actually an infinite number, because you could have the light bouncing inside the raindrop that many times. It can bounce all the way around there, and it can bounce. But every time every time this happens, the more complicated, more reflections, the intensity of the light coming out decreases. So you don't see anything beyond just the first and the second rainbows. The rest are sometimes there, but they're very vague. They have been observed in the laboratory, of course, with very intense laser beams. We sometimes see these additional colors inside the ordinary rainbow, and these are due to diffraction, not refraction. So this is optical scattering of light by the very small water droplets in the atmosphere up in the air. Now, what about this? How can this happen? Well, what's happening is the giveaway is this reflective water surface. So there's the ordinary rainbow, but of course you get a reflection. And this is the reflected rainbow formed by light being reflected off the sea. Now, if I was there, I'd ask, how many of you have seen this? Anybody seen this?
I've got one or two hands up.
Yep.
2 hands up.
2 hands up, right. Well, that's amazing, because I have never seen this.
3 hands up.
3 hands up, right. Well, this is a rainbow taken from an aeroplane. And of course, aeroplanes get high enough so that the surface of the Earth doesn't get in the way. We usually only see a part of the rainbow because the surface of the Earth is in the way. So from a balloon or aircraft, you get a circular rainbow. In fact, in this one, we've got the double rainbow as well. So I've never seen that. So that's a mystery to me. Now, this is a fog bow. It's rather like a rainbow, but it's caused by diffraction rather than refraction, the scattering of light by very small water droplets. It's a fog bow. This is a German word, Heiligenschein. So this is dewdrops on the ground. Overnight, you get dew on the ground. Go out and stand there, and you can see a glow around your head. And you think, gosh, why am I special? Why have I been picked up with this glow around my head? And then you take your camera and you move your camera over here, and you find that the glow is around the camera and it takes the picture. So whatever is taking the picture is getting the glow around this this Heiligenschein, and it's centered on the anti-solar point, the opposite direction to the sun. Now, this is a physics experiment. If you take a laser beam and fire it through a small hole, you will get a circular diffraction pattern. So when I was talking about diffraction, this is the effect of light being scattered by small objects. They could be water droplet, for example. And if you look up at the moon in the evening and you see this colored glow around the moon, then this is due to diffraction. And if you see it, then you know it proves that what is up there, this cloud, is made of water droplets. So even though it's quite high up in the sky, it could well be supercooled. They're not frozen, they are not ice crystals. But of course, if they were ice crystals, you wouldn't get this. You would get the 22-degree halo, which would be much, much larger. So remember, corona is due to diffraction rings. It produces these diffraction rings around the moon. Now here's another one, very interesting. You're looking out of your window in your airplane, and you see a glory, which is exactly the same thing as we've just been talking about, light scattering and diffraction by water droplets. It appears to be around the airplane. But what's interesting, if you were the pilot and you saw this, the circles would be centered around you. This is the chap who took this picture is obviously sitting here on the airplane. If he was sitting on the tail, it would be around there. Now, this is the Brocken spectre, which somebody sent me a photograph, and I think might be listening today. It's exactly the same thing. It's the shadow of the observer is cast on the cloud, and then you get this circular glory, corona, due to diffraction in the very small fog water droplets.
I think quite a few of us will have seen those.
Yes, I'm sure they have, yes. Makes you feel very special with that around your top of around your head. Here's another one. Now this one is iridescence. This is also diffraction, and it produces these wonderful colors. You do see them quite often, actually, looking up at clouds. Looking more like this more often. This is a particularly bright one, very, very special. This one is more how you see it, but it's diffraction, light being scattered by very small water droplets. These are nacreous mother of pearl clouds. Now, if we go back to the original diagram, at this altitude, you've got the mother of pearl clouds. So the temperature in the atmosphere is rising. This is where the ozone is, and this is where you get the ozone depletion effect. So these are mother of pearl clouds. Beautiful colors due to this diffraction, refraction, everything combined give this fantastic effect. These are more polar stratospheric clouds, sometimes called nacreous clouds, but very cold in the atmosphere. Now, up at the top here, we see noctilucent clouds, and these are night shining clouds, very high in the atmosphere. And there they are, noctilucent clouds. They could be small ice particles, they could be meteoritic dust, volcanic dust, tropospheric dust. The ice is coated with salts. It gives you these super vague looking clouds way up in the sky. More of them there. Now, this is something you get over mountains. Air rises over the mountains and produces clouds, and they're sometimes spectacular, like these piles of plates, they're called. And this one, I haven't seen this myself, but you do get cap clouds over mountains, a very, very symmetrical cap cloud. And I spent several years working in Wyoming, and there was one particular mountain there called Elk Mountain. Now, it had a cap cloud over it, which is why we went up to study the ice crystals up there. I never saw it looking as spectacular as this one over Mount Fuji. Sometimes the ice crystals form inside a regular cloud, and they deplete all the water droplets. The ice crystal will then fall down as snow, leaving a hole, cirrus fall streaks. Now, in the evening, the sun is setting, the sun is shining through gaps in the clouds, and you get these crepuscular rays, streaming clouds in parallel lines coming through the clouds. And you get anti-crepuscular rays. The sun is behind us. The rays are converging on the anti-solar point. So it's like parallax. It's railway lines converging in the distance. So look out for all those effects. And have you got any questions?
Clive, that was fantastic. I love looking up at the sky. I love looking at the sky in the daytime. I'm actually doing an Open University course about the science of the weather. So some of what you spoke about was very much what I've been trying to learn about. But there are some questions creeping out. So Cos, you had a question you wanted. Clive, have you finished your talk now?
That's right.
I'm wondering whether to ask you to stop sharing your screen, but then perhaps I shouldn't risk that, because then you might lose us all. How many faces can you see at the moment?
Just only you.
Oh.
Right, Carolyn should be able to click.
I can see Susie
screen.
now.
Right.
I can see
Carolyn should be able to stop the participant sharing.
Karen, can you stop?
I can stop sharing. I'll stop sharing, yeah.
Okay.
There we go, yeah.
Now what can you see, Clive?
I can see Susie, yeah.
Can you see lots of people, or can you only see?
I can see 6 faces along the top, and probably more. Yeah, I think more. Oh, right. Lots of faces, yes. Well, hundreds of people.
Let us all wave at you. So thank you for a fantastic talk. Cos, you wanted to ask a talk about the size of raindrops.
Yeah. I do have a question, but first, thanks for the talk, Clive. And I've just got a quick story before my question. It was.
Oh, you never tell quick stories.
All right. I was a teacher on duty at break in the playground, and this boy came up to me running quite excitedly. He said, "Sir, look at the sky! Look at the sky!" And I was there thinking, "Oh, hang on, is this a trick he's going to play on me or something?" But he was a nice lad. So I did look up. Right above my head was like a broken circumzenithal rainbow. It wasn't continuous, but it was like a rainbow had broken a regular one, and then floated up to the dome, top of the dome,
Yeah.
and formed this oak. And I said to him, "Thank you so much. You know, it was great. You know,
Yeah.
look up always."
Right.
So,
Did he know that it was a circumzenithal arc?
no, he didn't. He didn't. He just had that joy and wonder at it. I know. I'm glad I was there. So then I always got interested in it and seen. I've seen moon dogs and sun dogs, etc. As I'm sure other people here have been. But a question for me was earlier on in your talk, you showed a diagram with different sized water droplets. And being a maths teacher, I've seen the sort of classic raindrop with the light coming in and being internally refracted 1 or 2 times. But I never thought about what the size of a rainbow might, of a water droplet might make to the appearance of a rainbow. And would it have a difference on the quality?
Yes, if the droplet, if the droplets are very small, then that's what gave you the fog bow, due to diffraction in small droplets. But when they get a little bit bigger, so that the refraction effect can take place, then like a couple of, well, 1 millimeter, 2 millimeters, something like that, will produce a rainbow.
Oh, right, yeah. Thank you.
Raindrop size.
Yeah. What determines the size of a raindrop, though? I mean, what stops them from being as big as footballs by the time they get to the ground?
Well, gravity, I think.
Yeah, okay.
And you said that raindrops form on dust particles in the atmosphere.
Yes, that's where the water droplets come. Yeah, little condensation nuclei, the water vapor deposits on those, and they just grow. Yeah.
Are there some parts of the atmosphere above the globe where there are fewer dust particles, so water droplets are less likely to form?
That's why we went to Yellowstone Park. The air there is so absolutely pristine clear. You never get any water droplets. You just get beautiful ice crystals, clouds of ice crystals.
Because there's no dust in the sky.
Absolutely clean, yes.
Thank you. And I've got quite a queue of people wanting to ask questions. Francis, you wanted to ask a question.
I was just trying to be clear about the effect of light on the light at the poles. Is it because of the cold, or is it because of the cleanliness of the air? Because there seem to be some very special effects there.
You're exactly right. It's the same as Yellowstone Park. It is incredibly clean. There aren't all these little aerosols to make water droplets, but of course it is so cold that any water droplets formed will freeze. The temperature is below -20, and most water droplets will have frozen by that time. Yeah, so it's clean air and lots of ice crystals.
And Carolyn, you wanted to ask a question? Oh, sorry, Francis. Francis, have you finished? Was that?
No, sorry, just saying thanks.
Okay. Carolyn?
I'm absolutely useless at maths, and I just wonder if you could possibly explain this 22-degree angle in 46, because you had a picture of the sun, and round it were these halos. What was the 22-degree relative to?
Right, well, I showed a picture of a single ice crystal with a sun ray, light ray going into it, and it was refracted at the first surface of the ice crystal, 22. And again at the second surface of the ice crystal. And so it had been deviated by the ice crystal by an angle of 22 degrees. And when you have millions of these ice crystals, flat plate ice crystals with the sun coming into their sides and all being deviated by 22 degrees, then you get a halo.
Oh, right. So yeah, okay, that's great. A lovely talk. Thank you very much. I did enjoy your images. Thank you.
I think Jason is sat there on the edge of his seat wanting to ask you. Everyone else has said, can I ask one question? Jason's said, can I ask you some questions? So come on, Jason.
A second, let me unmute myself. Clive, I really enjoyed that. I've been looking forward to your talk for a very long time, because it's something that's fascinated me for years. Just a question. I think Phil may have sent you a couple of photographs that that I managed to dig out right at the last minute.
I did. Would you like me to share those, Jason, so everyone
Can
can
you
see
do
them?
that, Phil? Yeah?
Clive, have you seen the photographs? I emailed.
Yes, yes, I've seen them, but show them, yeah.
If I share them with you now, then
That,
can people see? Hang on.
Yes,
Can you see the? All you can
Clive,
see.
I'm
All you can see lots of people, or can you see the photograph?
yes.
Yeah, I'm hoping you can explain this, Clive, because it's something I haven't found any reference to at all. And we were walking down Spurn Head, you know, just off Hull, and we had the most wonderful halo display. There was everything going on. We had the, you know, the sort of the halos, the circumdental arc, the upper tangential arc, the sundogs. They were all a bit burnt out, but the two things that I really enjoyed seeing were the perhelix circle, which went right round the sky. But if you can see on the left-hand side, there was like a bow at the opposite side to the sun.
Jason, George, is this a full panoramic photograph?
It's a full, yeah, it's sort of 180 degrees of the sky.
180 or 360?
No, it's just over 180. It's probably
Right.
like about
Yeah.
2.
That's the sun there.
There's the sun, yeah, the very bright bit on the right,
Right.
but with the halo around it, which is all a bit burnt out. But if you look on the left-hand side of the picture,
Tell me when to stop.
there's like an arrow pointing up off that circle.
Right, well, across this horizontal line of that picture,
Yeah,
you can see the parhelix circle centered on the sun, goes right round the horizon. And of course, your wide angle view makes it look as though it's not bent, but it is. It goes right round the sky.
That's
And here we see one of the it's a sort of extra sundog, isn't it? There is another circle around here, which we don't see much of.
Is that where my mouse is now, Clive?
oh, I can't. Yeah.
This little spot here. Yeah,
Are
so
we
this
talking
is
about right at the left-hand side of the photograph?
It's like an upside down.
It's like a V. It's like an upside down V shape.
Is that where this is where the mouse is, Jason?
I
yeah.
can't see your mouse.
No, I can't see your mouse.
Oh, there you go. So at the left-hand side of the screen, there's an inverted V.
That's right. Yeah.
Oh, right. Okay. Oh, yeah. Okay. I see.
Now that's on the exact opposite side to the sun. Yeah, just there.
Yeah.
And I can't find any reference to it.
I think you've discovered something new. I've never seen that.
It was absolutely extraordinary, to the point where I think everyone thought I was crazy, because I was actually grabbing people as they were walking by and saying, "My God, have you seen this? You've got to have a look at it." But it was extraordinary. It was the most wonderful display, and we had virtually every arc I could think of. If you look in the center, you can just see some other points there which were getting brighter and sort of like you know, dimming, you know, it was changing constantly. But that was one that I've never come across, and even looking on the at Optic site, I couldn't see any reference to it.
I've never seen a reference to that. So yeah, I'll go and look it up.
Yeah, that would be great, Clive. If you could find out for me. I took it years ago, and that's why the camera isn't very good. But it's something I've always wanted to know.
Yeah, I think we'll call it a ghost.
Yeah, it's just like somebody had put a bow in the sky on the opposite side to the sun. So yeah, very strange.
Yeah.
Okay.
But Clive, if you do
Yeah,
find
well,
it, when I emailed that to you, I sent the email to Jason as well, so you could reply to him or reply to both of us.
sorry.
The email I sent to you with these photographs,
Yes.
Jason's email address, I sent it to Jason as well. So
Yes.
there is a means of. So Jason, did you have any other questions?
Yes, well, it's actually, I don't know. I don't know whether anybody's ever tried this. Sorry, it's not really a question, but
Do you want your other photograph?
yeah, do you mind putting my other photograph up?
Can you see that one? Can everyone see
yet.
that?
Oh, sorry, no.
Not yet.
I'm on port.
I've seen it. I saw your picture, the other picture. This is one of these.
Hang on.
I think I showed a very similar one.
Did.
Yeah.
Can you see that?
Oh, there we go.
Yes.
Yeah.
That's a Brocken spectre, and it's around whatever that thing is. You or
Yeah, that's me. Yeah, right.
That's you. Yes.
Yeah, but the unusual thing about this one is it's homemade. I drove up to the top of a hill once when it was very, very foggy, and
Yes.
put
As you do.
as you do, and put the car on full beam,
Yeah.
and then walked out into the fog, and you get quite a nice Brocken Spectre with a
Ah,
around it.
very
So,
clever.
it's one to try at home. That if you
Okay. Yeah.
So the light source there, Jason, is your car headlights.
that's right. Yeah, on full beam. Yeah.
So
And
you get two Brocken Spectres then.
Yeah, yes, you would. Yeah. And it was wonderful. Kept me occupied for a few minutes.
Oh, very good. Yeah.
Yeah.
Good.
Any
But-
other questions?
Yeah, I have actually got a couple of questions. Actually, do you mind? I'm hogging it a little bit. If anybody else,
It's all right.
Keep going.
okay, right. My main one was I must admit I've always loved noctilucent clouds.
Yeah.
Is there any sort of explanation for them now? Because it doesn't really seem to be any records, you know, going back in history. They all seem to be quite a recent phenomenon. Is it just that people didn't notice them, or do you have any explanation for that, Clive?
They are very rare. And there has been a lot of controversy about what's producing them. As I listed everything that everybody's ever mentioned, maybe ice crystals, maybe ammonia. So one of the favorite talks is that it's ammonia, little crystals of ammonia, or meteoritic dust, or just dust particles of different types. It's so rare that I don't suppose it's been really studied. I mean, you'd have to send a balloon up through them to take the samples, and I don't think that's been done. So it's a bit of a mystery.
So, I mean, I've heard some people sort of infer that it might be because we're sort of sending rockets and things like that up now. Is that at all possible, or?
Yes, because they pollute the upper atmosphere. They do with all sorts of heavy metals. Yeah, yeah.
So it might be quite a recent phenomenon then.
It's probably got more common since people have started launching rockets. Yes. Yeah.
Oh well, that's great. Thank you very much for that.
Any other questions?
Are you finished, Jason?
Well, there's a couple of others, but I mean, I'll let somebody else have a talk.
Susie, you had some questions you wanted to ask. Very question.
Just one question. I really enjoyed your talk and I loved all the pictures. Thank you. When you showed us the double rainbow, it was darker between the two rainbows. Why is that?
I think it's a relative thing. The rainbow is so bright that it makes it look darker, but there's also a sort of refraction effect, I think. But it's an optical phenomenon, and the rainbow is so incredibly intense that it makes the region behind it look much darker.
Ah, okay. Thank you.
And then the second rainbow is a mirror, is a reverse. The color, sequence is reversed.
Oh,
yes.
Never noticed that. Right.
Yeah. Yes, it is. Yeah. Thank you. Thank you. I only had one question. Thank you.
Do we have any other questions? I think
I've got another question.
Did Carolyn have a question?
I think Carolyn, did you want to ask any more questions?
No, I'm fine actually. It was just the one, but yeah, it was good talk.
So does anyone other than Jason want to ask more questions? I'll come back to you, Jason. Go on, Jason.
Okay, listen, you might hate this question, Clive. I do apologise before I ask it, but is there actually any evidence for ball lightning or not? Because anecdotally, I know somebody who thought they'd seen it, but I mean, is it a real thing or not?
My mother saw ball lightning, so it must be real.
Yeah. Well, it was my grandmother who saw it, actually.
Right, okay. Yes, I think there's some people think they've seen ball lightning, and it's called persistence of vision. They see a lightning flash stroke nearby, and it saturates the eye, and wherever they look, they see a bright light. And that's not really ball lightning, but a lot of people think that might be ball lightning, but it isn't. But ball lightning does exist. And there's a fantastic book I've got, a Victorian book. It's a picture of on the inside of a house, and the ball lightning went through a keyhole and killed all the little children inside. It was just awful. And the picture just showed their boots on the floor. They'd been blown up. It was just terrible. So ball lightning exists, but to be honest, it is completely not understood.
No.
Because you would expect it to be hot. Wouldn't you? The mind would say it must be hot, but it doesn't rise. It just drifts.
Really?
Actually, nobody knows what it is, but it exists.
How does it work?
And that actually went through the keyhole.
It
The
goes
house.
through, it comes down chimneys, goes through gaps in the window. It's unbelievable. Yeah.
Well, this is why
Wow.
it was a house across the road from my grandmother's, and it allegedly went down the chimney.
Yes.
And it didn't kill anybody, thankfully, but it made a hell of a mess of the house, you know.
Yes.
And
Luckily, nobody was hurt.
yeah, nobody was hurt, thankfully. But I mean, it was. But I always wondered whether it was really a thing. I mean, but
Yeah.
it is definitely documented.
It's a real thing. Yeah.
Yeah. Gosh, but no explanation whatsoever at the moment. I'm trying to nail you down. Any thoughts?
A friend of mine was in an aeroplane, and ball lightning went along inside the aeroplane. But he had a few gin and tonics, so we're not quite sure about it.
Oh, that's very interesting. Thank you, Clive. Yeah.
Jacinda, do you want to ask a question? We can't hear you.
Oh,
Listen, mute. Unmute.
He's not on mute. Jacinda, I think your microphone might not be working.
Or is the volume just down?
That's it, we can hear you now. No, sorry, Jacinda, we can't hear you.
can you type it in?
Jacinda, would you like to type your question into the chat and I'll ask it for you?
So the question, what are you going to ask?
Did I see Cos with his hand up again? I've lost Cos.
Yes, yeah. While we're waiting for the other line to be established again, on the theme of lightning, photographs of lightning look zigzagging. I've just got the impression that they just go from the top of from the cloud straight to the ground. But it occurred to me that they're really coming towards, some of these individual streaks are coming, zigzagging their way towards us, away from us, in all directions. In other words, my photos of lightning look very flat, as though they're in a 2D plane. But I've never seen a picture kind of showing lightning in 3D. Clive, what's their movement like?
Well, the little strokes that try to find their way to the ground, they go to pockets of the highest conductivity.
Yeah.
And of course, the atmosphere has got lots of electric charges in it, and the distribution of those charges varies. Sometimes there'll be a lot in one region and less in others. And so the lightning finds its way to the regions of most highest conductivity. And so it will, in fact, zigzag on the way down.
If I was above the initial starting point on the cloud and look vertically downwards, a bolt of lightning might go in throughout the whole 360 degrees possible before it goes to the ground.
It finds the path of least resistance,
Yeah.
literally. Yeah, highest conductivity, and that isn't uniform. That's right.
So where is it safest to be if you see a thunderstorm?
What? Sorry.
Where would you be safest if you found yourself in a thunderstorm? Where would you run to?
Given that the bolt from the blue can get you up to 10 miles away, there isn't anywhere, but you don't want to shelter under a tree or out in the open, flat on the ground, and discard all metal objects, they tell us.
Right. Jacinda has typed for us that he said he's seen 3 rainbows once.
Yeah. That would be that extra reflection.
Would that be over a water surface, or would that be still atmospheric effects?
If it was 3 genuine rainbows, it would be the second and third reflections which are causing that extra rainbow. It's very, very unusual.
but it is possible.
Yeah.
I mean, Joginder's also commented there's a description of a ball of light in the Golden Temple at Amritsar in India, where it entered from one door and went out through the opposite door.
Oh, that ball lightning. Yeah.
Yes.
Hmm.
So do we have any more questions?
Perhaps just on from what you were saying. Sorry, Phil. About you know, safest place to sort of stand. It just made me think about it. Is it actually true that if you're just about to get struck by lightning, your hair? Well, this is why I Phil, you'd be no good in this, I'm afraid. But that your hair actually stands on end or not?
I'm afraid you're exactly right. That is the first sign. If your hair stands on end and you hear sizzling, then you're definitely going to get struck.
Oh God.
How much notice do you get between these two effects? Not much, I suppose.
I was at a meeting once, and one of the young chaps was a farmer from Africa, and he was very annoyed that he was kept losing his cattle because they would go and rush and hide under a tree when there was a violent thunderstorm, and of course the tree would get struck by lightning and all the cattle would be killed. So he rigged up an alarm system so that when there was a thunderstorm coming in, it rang a bell, and he would go out and bring the cattle in. But he didn't need to after a while, because as soon as the bell rang, the cattle came in anyway.
Pavlovian.
That's extraordinary. Yeah.
Jason, have you finished?
I finished, sorry. Yeah.
So can I say that thank you so much for your talk. Who's playing music? Who's doing that? Oh. So can I say? I say thank you. Jason said he's been looking forward to this talk. I certainly have. I think many of us have, and I think we owe you a lot of thanks. We owe thanks for the talk itself, and thanks for letting us persuade you to deliver it to us in this format, which I think you were very unsure about at first. And I hope the experience has worked for you. It certainly has worked for all of us. And then I say thank you for being patient with us early on, patient with me early on this evening when I managed to get you to stop sharing your screen and start sharing your screen again. So if we were all in a room together now, you'd hear a loud round of applause. But